My talk is about an approach to actually approximate the accuracy of a profiler using machine code level slowdown. I did this work with Stefan Marr. Profilers. Profilers are tools that allow you to observe performance behavior. These can be characteristics of an execution. They may be such things as memory allocation, object allocation, or how much time did we spend in a method, such as something like that. There are many types of profilers, sampling or instrumentation-based, but we're only interested today in sampling-based profilers, which is where you periodically halt execution and you collect a sample, some information. This may be as simple as the program counter, and then you can look at the metadata and you can know what method you're in at that point of halting. There's a problem. If you actually run a program with a profile attached multiple times, you'll start to notice the profile will change. Sometimes a method may take less time, sometimes a method may take more time. An actual real example of this is we ran the Delta Blue benchmark 30 times with async profile attached, and we just overlaid all 30 runs on top of each other. The error bars there are just showing the range of measurements we got. All methods that are highlighted in red are methods where in at least one run they were the hottest method. They were the method that consumed the most amount of the runtime. If your goal of using a profiler is to try and identify what is the most important method, this is not a very clear picture to actually understand that. And when you want to do some manual optimization, it's not entirely clear which method here you should target first. Why do we see stuff like this? Well, there are multiple reasons. Non-determinism. Compiler decisions, garbage collection, and interrupts can all influence how a program is executed. On top of that, the tools like profilers suffer from the observer effect. Work done by us and others has found that profilers, samplers, and instrumentation can actually influence an execution of a program, and this can dramatically change the execution, giving you an unrealistic view of the program, an execution that would not normally happen if there was no tool attached. What do you do? So you need to test, if you want to test a profiler to see how accurate it is, you need some sort of stable ground truth that you can test against, some known performance behavior that you can be certain exists. A possible solution to this is slowdown. Slowdown is where we deliberately introduce measurable and controlled changes into the program to make the program run longer. Specifically, we're trying to make the methods run for a longer period of execution. We're not changing the logic or the semantics of the program, we're just establishing a new program behavior. It is an approximation of the program behavior. How do we actually slow down a program? Well, we're targeting at the basic block level. That is just a way to organize machine code where you have one entry point and one exit. This is terribly useful to target for slowdown because it means once a block is executed, our slowdown is guaranteed to be executed. We're targeting basic blocks almost at the very end of the compilation pipeline, so we're way after inlining and dead code and loop transformations, so we should have a minimal effect on compiler decisions. The type of slowdown we're using are wasteful MOVs. On the right, highlighted on line 3 and 5, you can see we've added these MOV which perform a movement from the same register to the same register. This should not change, this will not change the value in the register, but it will cause the CPU to waste some cycles in having to deal with these. To determine actually how much we add, how many of these wasteful mods we add, we're using hardware counter feedback. We're using vtune, which we progressively will add slowdown and use the vtune report to actually see how much slowdown we've caused, and that should give us a more accurate number of how much we're adding. The research questions we had in the paper were the following. Does slowdown at a block level result in accurately slowed down programs? So this is a test on whether or not we can actually achieve and target slowdown. We chose 3 target slowdowns of 50%, 100%, and 150%. And we wanted to see how close can we actually get to that target slowdown. The next one was, do sampling-based profilers report the same percentage of runtime for identified methods? This is testing whether or not our approach has any side effects. Even though we're making the execution 100% or 150% longer, you would still expect the ratio of time spent to methods to be the same. The percentage of runtime for each method should still be the same, they're just X amount longer. And finally, do sampling-based profilers accurately detect changes to a slowdown method? This is actually the real test of, we can now evaluate profiler accuracy. We're going to deliberately make parts of the program run slower, and we can evaluate profilers on whether or not they can detect that slowdown and how accurately they detect that amount of slowdown. Our experimental setup, we're using Java, we're using the Burchell compiler, which is a just-in-time compiler. Specifically, we're making use of compiler replay. This is a feature Burchell has where for a given execution, you can get it to log what compiler decisions were made, and then you can refeed that into it for the next execution. What this should give us some level of stability in compiler decisions and should make our results a little bit more stable. We're using the 14 benchmarks from the Are We Fast Yet suite, deterministic, 5 macro, 9 micro. Each benchmark execution is 500 iterations, with each iteration being about 100 milliseconds each, and we will repeat that 10 times for each benchmark for each profiler. The 4 profilers we're using today is Async Profiler, Java Flight Recorder, JProfiler, and YourKit. So, for the first question, do we accurately achieve slowdown? So, for our 3 target slowdowns of 50%, 100%, and 150%, yes, pretty much. For 50% and 100%, our medium is bang on those targets areas, with only a variancy around 5 to 10% between each benchmark. For 150%, we've slightly underslowed with the medium, 146%, but that is well within, and we believe it is achievable to increase the slowdown. So underslowing is not the worst possible problem. Do sampling profilers report the same percentage of runtime? So this is a test on whether or not our approach has any side effects. Have we changed the performance behavior? When we pointed profilers at the program before slowdown and after slowdown, and we measured the percentage of runtime for each method. And we're plotting every method's percentage of runtime. Now, if they have remained the same, they should be on the x equals y line, because it's the same ratio. For the majority of the benchmarks, this is true. It is, in fact, 13 out of our 14 benchmarks. The methods all remained within 5% of that line, which is definitely within noise variance. As you can see clearly, though, list benchmark, that backwards triangle, is off the line. It has the amount of time we spend in list has changed when we slow down. And this was true for all 4 profilers we tested. Why did we see this behavior specifically in lists? Well, we took a look at the amount of debugging information available in each basic block, Lear instruction for each benchmark, and list had one of the lowest amount of debugging information, 70%. We also specifically looked at some of the hottest blocks. List have those are the blocks with the highest amount of execution time, the blocks we spend the most amount of time, and we found a severe lack of debugging information. In fact, one of them which encompasses double digits of percentage of the runtime, had no debugging information. Specifically in JVM profilers like samplers, when they hit an instruction with no debugging information, it has to guess. It has to look at the nearest instruction, nearest debugging information, and use that for the association. And what this meant was when it hit our slowdown, it sort of exacerbated this problem. It meant that all of our slowdown had to be guessed in what debugging information it had. Do sampling profilers accurately detect changes in slowdown methods? So this, knowing now that our approach is accurate and it has minimal side effects, we can now test whether or not profilers accurately detect increase in runtime of the program. So we added 5 seconds of additional runtime to select target methods, specifically targeting individual basic blocks that solely belong to that method, and we added slowdown to those blocks, and on top of that, we added debugging information to our slowdown to guarantee that slowdown was correctly associated. And we tested whether or not profilers would now associate that additional runtime with the targeted method that has been slowed down. One of those tests is here. We made vector.hasSum 5 seconds slower, and we looked at if all 4 profilers would correctly identify whether or not this method has now got slower. Async and Java Flight Recorder, oh, and I must mention, because we knew the overhead and we knew the exact amount of slowdown we're adding them to an accurate amount, we actually could predict the amount of additional change we would expect. So that actually gives us a degree of accuracy we can evaluate a profiler against. Async and Java Flight Recorder have identified correctly that vector.hasSum has increased in its runtime, and Async's definitely within our prediction, and Java Flight Recorder is a little bit off, but it's definitely close to our prediction. JProfiler has not detected any increase in runtime in vector.hasSum, and instead has completely changed the result and has decided that vector for each is now slower, even though we didn't slow it down. And YourKit, most surprisingly, has actually detected a tiny change. It's now saying we spend a little bit less of the runtime in that method than we did before. So this is our practical way of actually evaluating profilers to a degree of accuracy. So to conclude, measuring performance behavior is hard. You have to contend with the observer effect and non-determinism. Program slowdown enables us to approximate the ground truth. It gives us something measurable that we can look for in a profiler. Our approach to slowdown is accurate, and it maintains the program behavior, performance behavior. And approximating the ground truth enables us to detect inaccuracies in profilers. I'd like to thank JC Designs and the University of Kent and Stefan for this work. If you were interested, please have a look at the paper. That is the end.
So we do have time for some questions.
So you mentioned that the slowdown is being introduced after optimizations like inlining. So when you're trying to slow down a particular method, how do you make sure that you've hit every place maybe that it's being used?
We target every basic block in a program, every single basic block. Every single basic block gets an equal amount of overhead, so every block will be 100% overhead. We're not just targeting one place. We distribute the slowdown within the block, and what that means is when certain instructions in a block have different debugging informations, our slowdown should be hopefully close to whatever method that it was there. It's not perfect, but you can't know, with hardware counter sampling, you can't know to that degree of every instruction the correct amount. So the balance.
For the final thing though, you were like specifically slowing down vector.hasSum.
Yes,
right?
that one, we added debugging information to try and give the profiler the best chance of actually seeing it, because the sampler should hit that slowdown and it has the debugging information. So it's not guessing, it's just at that point, does the sampler correctly sample at that point and associate?
I see. So you guaranteed that anywhere that your slowdown was, a profiler should have associated that with vector.hasSum.
Yeah.
I see. Thank you.
Yeah.
Thanks for an interesting talk. How would your profiling approach cope with separately compiled code, say from JNI or something like that?
That is a very interesting question. I can't actually answer that at the right moment. I'll talk to you offline about that one specifically, sorry.
Maybe a last one?
Sure. Do you have any clue why the profilers sort of give these weird results, right? You clearly showed that there's something funny going on. Do you have any clue what?
There is a few reasons. Sampling skid is a good reason why they can be quite wobbly. The actual delay between when it actually halts and actually collects the sample, and there's a paper that I can't remember the name of it, but it proves that you can have very hot loops that can never be sampled because the skid always jumps over it. So there are cases where there is still a degree of sampling bias that exists where some areas don't actually get sampled and therefore they're biased to certain areas.
So in a sense, it's a bit of an incompressible problem.
Yeah.
Okay.
Yeah.
Thank you.